Let us get back to 1930s, 40s, perhaps, when people were thinking about the following questions from communications perspective and many other applications. I am given a continuous time signal, analog signal. Is it possible for me to sample this analog signal and use the samples for further processing? In the process of sampling, can I reconstruct the analog signal perfectly? Right? These are the questions which were hounding these people in the 1930s and 40s for most of the communication engineers. And one such brilliant idea came from Shannon, and I will just state the ideas here. So let us start with the following. Let x of omega be the spectrum of x of t. Right, x of t is a continuous time signal. X of t is 1 upon 2 pi integral minus infinity to plus infinity x of omega e j omega t d omega, and we know this. This is x of omega is the Fourier transform of x of t, and then you can get the x of t from the inverse Fourier transform. Now, if x of omega is assumed to be 0 outside, the band modulus of omega is less than 2 pi times b, right, then we can write x of t as 1 upon 2 pi integral minus 2 pi b to plus 2 pi b x of omega e j omega t d omega. Just straightforward. I mean, you can think about why we need to make this assumption here about the band limitedness. I mean, most signals are band limited. I mean, you think about speech signal, you think about most natural signals, they are band limited, and even if they are not band limited, by filtering you can make them band limited. Okay. Now, let small t be n upon 2 times b. Therefore, I can get the samples x of n upon 2b as follows. So, this is basically 1 upon 2 pi minus 2 pi b to 2 pi b. So, basically the continuous time t is replaced by n upon 2b. This is x of omega e j omega n upon 2b d omega, right. Now, you have to really interpret this. The left hand side has x of t at the sampling points the integral on the right, which is this, is essentially nth coefficient in the Fourier series expansion of x of omega over the interval minus b to plus b as a fundamental period. Right? I mean, this is the way we interpret this this equation. Now, x of n upon 2b, I think this sequence that we have for n equals 0, 1, so on, these determine the Fourier coefficients in the series expansion of x of omega. Now, since we assumed that x of omega is 0 for frequencies greater than b and x of omega is determined fully if the coefficients are known, right, we can say that the samples x of n upon 2b determine x of t completely. Right? We started off with the spectrum and then linking with the continuous time signal, then basically sampling and then interpreting this as basically the Fourier coefficients, the series expansion of the spectrum. Right. So, one of the questions that naturally comes to us is, how do we construct, or if you want you may add the word reconstruct x of t from the samples. Right, our intuition tells us we should have some kind of interpolation filters, right. We have these samples and there should be some interpolation filter which has to go through these samples, and it has to be the right interpolation filter if we were to reconstruct this, right. So, we will try to get towards this idea more formally within a mathematical framework. Okay. You have a basic idea now. I take a spectrum, I sample the, I take the spectrum and I look at the Fourier coefficients in the series expansion of the spectrum, and I get these values, and how do I interpret these values as, right. And the other question is, I have these samples, can I get my continuous time signal back. So, let us start with some very basic stuff that you know from signal processing, right. We will start with with the Dirac Coombe function, Coombe because it is really a Coombe, I mean Dirac function because a delta function, and if you have a train of the delta functions, it is basically like a comb, right, comb that you use for your combing your hair. Now summation n equals minus infinity to plus infinity delta of t minus n times capital T is this Dirac Coombe sequence, and the sequence is periodic, and since the sequence is periodic, it has a Fourier series representation. I mean you can just get the exponential form, right, you can write it as some Cn times e power j 2 pi k upon capital T times small t, and you can figure out this coefficient Cn, right, and if you solve for this, Fourier series representation. Okay, now this Cn you can compute it to be 1 upon T. Okay, it's very straightforward, just plug in the formula for the exponential series Cn equals integral from T naught minus T by 2 to plus T, just get the integral form, and then you will get to solve these Cn's, straightforward. Small typo here, this has to be Ck here, not Cn. So let us change the subscript, this is a Ck and this is a Ck here. Okay. Now basically we can say that this is 1 upon T e power j 2 pi k upon capital T times this T, and this is basically Fourier pair, and you can write this is 1 upon T summa k equals minus infinity to plus infinity delta omega minus k upon T. Right, Fourier transform pairs. Now let us consider summa k equals minus infinity to plus infinity f of k, just the Fourier coefficients. So I have the summation k equals minus infinity to plus infinity. Now f of k, I replace it by this integral, because this is how I would compute the Fourier coefficient, right, Fourier transform f k. Now this can be written in this form, assume I can do the exchange. So I have minus infinity to plus infinity f of t summation k equals minus infinity to plus infinity e power minus j 2 pi k t. Now you can say that this summation can be replaced as, I will put this in pink, summation n equals minus infinity to plus infinity delta t minus n. Note that capital T is 1. If you go in this form here, put a capital T here. If the T equals 1, you would have this form, right. So, therefore, I can simplify this equation as, now again I do this exchange back, sigma n equals minus infinity to plus infinity, then integral minus infinity to plus infinity f of t. I think when I have an integral, I have to put a dt here, right. It is something to be careful about. Okay, now so I exchange this back again, assume this exchange is possible. Now this is delta t minus n dt, and this would exist when t equals n. Therefore, this is basically summa f of n, right. We are now we have linked the time samples to the frequency sample, the summation, right. Now, let us sort of go one step forward. Similarly, consider a periodic sum s of omega plus k upon t. This is basically sigma k equals minus infinity to plus infinity. I have a spectrum here, basically I take some periodic copy essentially of the spectrum, right. This is what is happening here. This is how I would interpret this sum. Now, this is basically Fourier, because Fourier transform is a linear transform, right. This is I can take the Fourier here, Fourier of s of t e power minus j 2 pi k upon capital T times small t. This is just basically the modulation property, right. So, this can be interpreted as the Fourier of s of t is taken outside because there is no index k here, summation k equals minus infinity to plus infinity, right, e power minus j 2 pi k upon t capital T, right. Because the Fourier transform is linear, I can just this is I am making use of linearity here at this step. Now, you can interpret this as t times summa n equals minus infinity to plus infinity delta t minus n times capital T, right, because from our relationship from starting with the Dirac sequence. Now, this is basically the Fourier transform of s of t times capital T times sigma n equals minus infinity to plus infinity delta t minus n times capital T. Now, these things are existing for t equals n times capital T, right, otherwise it is vanishing. So, therefore, this t I can replace as nt and roll everything in the summation. So, I can write this as the Fourier of summation n equals minus infinity to plus infinity s of small n times capital T times delta t minus n times capital T, right, because this exists at t equals nt, not otherwise. So, therefore, I will pull this here. Now, I can say that the last part is basically summa n equals minus infinity to plus infinity t times s of n times capital T times the Fourier of delta of t minus n times capital T, and I can interpret this as t times s of n t, that is I am having samples of the signal and then linking them with this modulation term. Well, if you follow the convention that omega is 2 pi f, we just have this to be f